first did you do the solve the problem? So yesterday we, okay, good. Then tell me what is the expression for this transfer function t, or what is the value of t?
Yes, ma'am, 1 second.
Yeah. So can you give me the expression for V out by V in? Someone said no, that you have already solved. So just give me, just tell me the expression.
Ma'am, I tried. I got it as V out by V in to RF by RF plus R in. RF by RF plus R in.
RF plus R in. Okay, so first of all, you see the question here is that you have to find the sensitivity of the value t of this function t with respect to changes in A and beta, right? So that means, so first thing is that you have to find t as a function of A and beta. Okay, why you need to find it as a function of A and beta? Because the expression for STA, it goes like you have to do like delta t of delta A and then multiply it with A by t. Right, so you need an expression. So this R, so you can just substitute this value of RF, but you can make substitute RF and R in. You can divide them, and beta is given by R in by RF. So if you just divide the whole thing by, so it will, from your expression, it will come as 1 plus R in by RF. So that means this should come as 1 plus beta, right? I mean, according to your expression. So you have to find out an expression which comes like this. But here you have, so where is your A term? Have you considered A as like infinite, or because otherwise you should get a term A also in the, so A means what? So you have already read this in basic electronics. I think you have read this op amps and all, right?
Yes, ma'am. A means
Okay.
amplification factor.
Yeah, A is the amplification. So that means what will be the value of A? So this is like go
V out by V in.
V in or Vn? Which one? The voltage as at the inverting terminal or the input voltage? Now you are talking about only the gain of the op amp.
Ma'am, inverting terminal it should be. So V in minus R in I in it should be.
So it should be. So ideally the value of A should be. So if you do so so value of A should be, so first of all it is going in the negative or the inverting terminal, so that means a minus sign will come, and then the value of A is only defined by this V out and the voltage at this inverting terminal. Okay, so that means if you write, so it should be V out not by V in, it should be by V, let's say if this value is Vn, so it should be minus V out by Vn. V in, because there is another term coming here. V in will come into picture when you have a feedback path which is already connected. So if you have A equals to minus V out by V in, and if you write the basic equation, so the basic equation goes like so I in plus IF would be equals to 0, because no current should flow into the non-inverting terminal of or into any terminal of the op amp. So I in by IF plus IF should be equal to 0. This is your one expression. And the second expression is, so for that, if you carry out a loop equation, you can write V in minus Vn divided by R in, or you can just substitute I in by, so I in would be V in minus Vn by R in, and your IF will be V out minus Vn by Rf. So this should be equals to 0. Am I right?
Yes.
Okay, so now if you have this equation, so from this equation you can simplify and you can substitute the value of A as V out by Vn, and from there you will find what the value of T. So ideally, so actually this expression is true, but it will, so first of all there should be a minus sign, and this is true if you take into consideration that A is infinite. But here the value of A is that is pretty large, but it's still a finite value. Okay. So if you solve this equation, then you will get the value of T. So the T is V out by V in. So that will come as minus A by 1 plus A beta. Okay, so now once you have, so now you have expressed T in as a function of A and beta. So then you can just simply use these equations. You can do the derivatives with respect to A, and then similarly for ST of beta, you have to do the derivative with respect to beta, and then you will find out what is the value of the sensitivity of the overall transfer function or the overall system with respect to any changes in the open loop gain and any change in the feedback gain that we have. Okay.
Yes.
Am I clear? Okay. So just to make one thing clear for you, so these kind of problems you should like you can go and look into the textbooks and you will find similar kind of examples. So you have to practice these kind of problems, because at the end of the day when you are giving the exams, these kind of problems will be coming, and then if you at that point of time, if you haven't practiced these problems, then it will become difficult for you to solve at that moment, and I mean think and solve at that moment. So it would be better if you can do some practice of these kind of sensitivity analysis. So if you go to the book, there will be lots of examples, so like solved examples are there. So you just try to solve them on your own without seeing the solution in the book, and then practice on your own. Okay. So the second problem
for it, ma'am.
Books, like I have shared the syllabus, right? In the syllabus there are a few. Yeah, so you can mostly you can look in that control systems engineering book by Nagaraj Gopal, that one, and also you can have a look at there is another book by Ogata, so that is modern control engineering. So in that book also you can see, but mostly I think for these kind of problems, Nagaraj Gopal is the best option. You will get lots of solved examples on this sensitivity analysis and all. So you can have a look at those.
Yes, ma'am.
Okay. Yeah. So now for this equation, so did you, what will be the linear form of this equation using this Taylor series expansion?
Ma'am, this one I haven't tried, ma'am. I'll do it now. I forgot it.
Okay. It's okay. You can try it now also. So the expression goes like, if you do the, if you write the Taylor series expansion. So now here if, so this is a function of x1 and x2 both, right? So if you do the, so can you tell me the equation? Or let me write it for you. Then you have x1 minus x1 bar right, and we are here actually we are ignoring the higher order terms, like is the second order derivative terms we are ignoring here. So from here you have to find, so tell me what is the value of f of x1 bar and x2 bar.
Ma'am, x1 bar is 7.
Delta f by delta x1 at x1 equals to x1 bar.
Ma'am, here in x2 also you should substitute the value, no, ma'am?
No, first of all you find the expression of delta f by delta x1.
Ma'am, it
So
will
what
be
is the
2x1 plus 2x square, x2 square minus 5 minus 8x2.
Why will the x2 term come?
Oh, sorry, ma'am.
Because
2x1 minus 5 it will be.
Because we are doing partial derivative, right? So in case of a partial derivative, all the other terms are considered as a constant. So that means only derivatives of that corresponding term will come. So it is 2x1 minus 5. So that means it will be equal to, so if you substitute, so here you will have expression only in terms of x1. So you will substitute x1 as, what is the value of x1 bar? 5. So that means it will come as 5. Similarly, delta f by delta x2, what will be this expression?
Ma'am, 4x2 minus 8.
4x2 minus 8. So this will be equal to 8. So then what will be your final expression? Did you get this expression?
Yes, ma'am.
Okay. So is it clear to the others also? So I'm only getting response from one person. So is it clear to others also? Okay, since there is no response, I'm assuming yes or no. What did you say?
Yes, ma'am.
Okay, fine. So we were discussing about this non-linear spring. So in case of a spring, so if we are talking about some small value of extension of the spring, so you are applying some force and the spring is getting extended. So if we are dealing with a very small value of this kind of extensions, then a spring behaves in a linear way. So that means the force which is applied to the spring, that is equals to F, will be equals to K times Y. So K is the spring constant, right? But however, if you move on to like very high forces, so which will result into very high value or large values of Y, in that condition, the linear spring law, that is not held true anymore. So what happens is that the spring law changes and it follows a nonlinear equation. So that nonlinear form is F equals to Ky square. So now let's say that you are providing some input or you are having, so first of all you are providing some force Fs1 which is in the linear range. So for the force Fs1, so the expression will be K into Y1, and you are applying some other force Fs2 which is of higher value, and for that value you are getting a larger extension, that is y2, and that expression is given by Fs2 equals to Ky2 square. So now if you are applying a total force of Fs which is equals to nothing but Fs1 and Fs2, in that case you will see that the expression will be Ky1 plus Ky2 square. So and this you can say that this is not equal to the total like y1 plus y2 whole square. So this is not equals to Ky square by y equals to y1 plus y2 whole square. Okay, so that means that we can say that this relation is not following the superposition theorem. So that means the overall relation of this of the spring is a nonlinear one. Okay, so now let us say that you have a system where you have a mass and you have a spring attached to it. Okay, so the mass is attached to a spring and there is some viscous force between the while the movement is happening. Okay, so in this case what you need to do is that whenever you have a mechanical system, the first step of doing the analysis is you have to draw the free body diagram. Okay, so the free body diagram means you will have to draw all the forces, you have to draw all the direction of the forces and the magnitude of the forces which are being applied on the mass. Okay, so now for this one, the gravitational force is occurring in the downward direction, and the force due to the spring that will be in the opposite direction. So for here the force will go in the opposite direction, that is upward. So that is given by, so since we are considering a non-linear spring, so that will be given by Ky square, and for this viscous friction, that will also be opposing the direction of motion, so that will also be in the upward direction, or and that will be given by F into y dot. And so that means the overall force which is being applied on this mass, that is nothing but mg minus Ky square minus Fy dot. So mg minus Fy dot, if you take these two terms in the other direction, and that will be equals to the overall force. So that overall force is nothing but the mass into the acceleration, or because of which the displacement is happening. So now you can write that let us say that we have reached a steady state condition. So that means the mass is not moving at all. Okay, so at that condition, let us say the value of y is equals to y0. So now at this condition, obviously since the value of y0 is constant, so that means all the derivatives of y0 will be equals to 0. So that means the first term and the second term, these two terms will become 0. So once these two terms become 0, so you can write mg will be equals to k y0 square, and from here you can find the value of y0. So in the next step, now let's assume that now the system is moving by a very small value, which is known as by a value of delta y. So that means now the value of y is now changing to y. So y is now equals to y0 plus delta y. So now this is no longer constant. So again, now we from the basic equation, we'll substitute the value of y over here. So you will get m d2. So you will substitute these values, and so this is the expression that you get. Now here you see that for this nonlinear spring, you have the expression k y0 plus delta y whole square. Now what we'll do is that we'll try to linearize this whole system. So for linearization, what we'll do is that we'll do the Taylor series expansion of this nonlinear term. For doing that Taylor series expansion of the nonlinear term, so that that gives us y is equals to k y0 square plus 2 k y0 into delta y. You can see how this term is coming. So once you have this term, now what you will do is that you will substitute this expression in the previous equation. So the previous equation now comes as mg this thing plus, instead of k y0 plus delta y whole square, now we have k y0 square plus 2 k y0 into delta y. Okay, so from this expression, obviously, first of all, the derivatives of y0 becomes equals to 0. So this term goes to 0. So now you're left with m d2y delta y, these terms, and there is mg on the left hand and k y0 square on the right hand. And in the previous slide, you have seen that mg at the steady state condition, the value of mg is equals to ky square. So this mg and ky y0 square, these two gets cancelled out, and you get a linear relation, that is m d2 dy2 of this expression, which is equals to 0. So here, using this Taylor series expansion, we are sort of linearizing the system from a non-linear expression. We are moving into a linear equation. Okay, so here you can see that the spring behavior, if you consider the spring behavior about a very small movement around the operating point. So that operating point is, so this is my operating point, the value of y is y0, and the value of force is, let's say, Fs0, which is equals to mg. So around that operating point, the whole system is linear, and the spring constant is now changed from previously the spring constant was k, and in the modified linear system, the spring constant is modified to k into 2k into y0. And this p0 point, that is known as the operating point of the whole system. So now if you, so this kind of modeling is basically, or this kind of this technique for linearization is known as a small signal modeling. And this is valid only if we are dealing with a very small change in the output signal about a fixed operating point. Okay, so with this we will finish the first module of the course, and then we'll move to the second module. So in this module, we will be talking more about different components of which are present in a control system, and then we'll see how we have seen how we are representing a system using a block diagram. So then we will also see like how this, so a system can be a complicated system. So the representation of a system can be the blocks which are arranged, that not necessarily it will be in a very simple way. So there will be like multiple interconnections of the blocks. So then from there we will see how you can do some, you can analyze that complicated block diagram and come out with the and figure out what is the transfer function of the systems. Those things we'll slowly study in this module of the syllabus. So first of all, let's talk about the control system components. Okay, so basically a closed loop control system. So we have seen that a closed loop control system, it consists of, there are like three main elements. So one is the feedback element, then there is the controller, and then there is the system which we are trying to control. Okay, so if you draw the basic block diagram of a control system. So here you have This I think we had drawn earlier also, but just to recap. Okay, so this is my reference input. Okay, this is the error detector. And the output of the error detector, that is, let's say that is EA. So this is known as the actuating signal. And this actuating signal is the input to the control elements. And this error detector and the control element combined together is known as the controller. Okay, the output of the controller is a control signal. And this control signal acts as an input to the plant, or you can say process, or the system that we are trying to control. So controlled system. Okay, and this is your output signal, and here you have the feedback element, and this is the feedback signal which is compared with the reference input into using this error detector. Okay, so this is the basic block diagram of a control system. So now just to elaborate a little bit more about the components. So this feedback element, that is basically this is a device which converts the output, that is the controlled signal that we have, into a suitable into another suitable variable which is known as the feedback signal, and this feedback signal is basically compared with the input signal using the error detector. Okay. Then the controller. So the controller consists of the error detector as well as the control elements. So now the error detector, we have already talked about that it compares the feedback signal with the reference input, and it determines the error signal or the deviation, or you can say the actuating signal. Now this actuating signal, it goes as an input to the control elements, and this actuating signal is basically manipulated and modified by the control elements in order to produce a particular control signal. Now this manipulation or the modification of this actuating signal which is happening inside the control elements, it can include like multiple steps. There can be, so the manipulation can be in form of amplification. There can be, it can be in form of generation of some suitable function such that that is suitable for powering up or suitable for application in the to the plant. And also there is a power stage. So this power stage is basically necessary such that the control signal is of that has sufficient power that it is able to drive the subsequent plant which is present. Okay, so and this so in case large power amplification can also be involved in the plant or the process which we are trying to control. Okay. So now if you look into the sensor components, so the or the controller components. So first of all, it will have a sensor. So in the controller, so these sensors are basically low power transducers, and they produce an output signal as a measure of the control variable. Okay. As you can like, as it is very apparent that any kind of linear proportional relationship between the input and output of the sensor, that is obviously always preferable, because we always want, because linear equations are always easy to work with, right? And then these sensors, they are mostly used for measurement of position, velocity. Then you can use them for acceleration, pressure, temperature. Then even in a chemical plant, it can be used, not necessarily that it has to be a physical or an electrical parameter. It can be the chemical state of the analytes or the reagents which are present in a reactor. And the output of these sensors are usually in an electrical form, and either it is in an analog form or in a digital form, but mostly they are in the electrical form. Now the second component is differencing and amplification. So what is differencing? So differencing is that the differencing is done in order to get the actuating signal or the error signal, and amplification step is used because we need to amplify, or we need to increase the value of this error signal to such a level such that to a suitable level both in magnitude and power, so that it will be able to power up the subsequent stages. Okay, so mostly op amps are used for differencing and for stable amplification over a wide frequency range. And these power transistors and this SCRs, that is the silicon control rectifiers, these are mostly used to provide a very large range of voltage or current or power levels at the final stage. So depending on what the requirement of the plant is, the control signal, the controller will generate a suitable control signal, and for generation of that suitable control signal there are these multiple steps which are present inside the controller, which work hand in hand, and the final control signal is generated. Okay, so now there comes actuators. So these actuators are basically these are devices and which whose output is a mechanical quantity. Okay, so either it's a translatory motion or a rotatory motion. So these actuators, they can be of different types. They can be electrical, they can be hydraulic, pneumatic, and the function of these actuators is that they will be able to perform tasks, like they would be able to manipulate the controlled process or the plant that we are trying to control. Okay, so how these actuators they control the plant is that, let us say that you have a chemical process or a hydraulic process. So these actuators will be able to either, depending on your input and what is your desired output, depending on that, the actuators will either open or close a valve which is present in the system. Or it might turn in case of a robotic system. So it might turn a robot link with respect to the neighboring links. Or if it is an electrical system, it might be able to move the transformer tapping up or down depending on what is the requirement. So this actuator basically it manipulates the controlled process or the plant. So in general, these electric actuators, or rather motors, they are used because they are generally used because of the fact that they are very flexible. Flexible in the sense that electric power is can be transmitted over a long distance through cables very easily. Okay, so because of this flexibility, and also the speed torque characteristics in a motor is very linear, so which is a very desirable characteristics. So because of these two factors, electric actuators or motors are generally used in control systems. But in case there is a situation where the speed, we are working with a very low speed and high torque applications, in those cases we generally do not go for electric actuators. People are still using hydraulic actuators. Okay, and then there comes the electrical system. So the electrical systems so there are like two kinds of electrical actuators. One can be the DC motor, one can be the AC motor. So in case of the DC motor, the problem with the DC motor is that it is very expensive, and although it has very linear characteristics, it has higher stalled torque is to inertia ratio. So all the other parameters are very desirable in DC motors, but the cost of the DC motor is one of the major disadvantages. So what do you mean by high stalled torque is to inertia ratio? So the torque which is generated by the motor when it is stationary, when at full applied voltage, that is known as the torque. So if you have high torque is to inertia ratio, that means that the so the time constant of the motor is less and the system will have faster dynamics. Okay, so these are some of the components that are present in any controller or in a control system. So now we'll talk about a little bit about the different kinds of feedback sensors which are generally used in a control system. Okay, so first of all we'll talk about something which is known as tachometer. Okay, so tachometer is basically it's an electromechanical system or an electromechanical device, and it converts mechanical energy into electrical energy. Okay, so this tachometer basically it works on the principle. Essentially, it works as a generator, and the output. So the output of the tachometer is an electrical signal, that is some electrical voltage, and the input of the tachometer is some rotational rotational speed or angular velocity. Okay, so what the tachometer is doing, that it is converting the angular speed or angular velocity into a proportional output voltage. Okay, so this is the main function of a tachometer. So basically, so as I have told, that it works as a generator, and the output voltage of the tachometer, that is basically directly proportional to the angular velocity. So if you want to measure, suppose some machine is moving, so you want to measure what is the speed of that machine. Okay, speed of rotation of that machine. So what you will do is that we'll connect the shaft of this tachometer, that will be connected to the machine whose velocity we are trying to measure, and from depending on how much that machine or that motor is rotating, or at what speed that motor is rotating, depending on that we'll get an output voltage which is proportional to that speed. Okay, so in case of a tachometer also, there can be a DC tachometer, there can be AC tachometers. So the most common form of DC tachometer, it mainly consists this iron core rotor. Okay, so how this tachometer works is that first of all you will have. So basically, so this is the so you have two permanent magnets, and the magnetic field is provided by using this permanent magnets. So no external voltage supply is needed for generation of magnetic field and anything. Okay, so this, and between the two poles of the permanent magnet, the rotor. So this is the rotor of the tachometer. So this rotor is placed between in the magnetic field between the permanent magnets, and the windings which are present on the rotor, that is connected to a mechanism which is known as a commutator and brush mechanism. Okay, so this commutator and brush, so from this brush actually there is an electrical circuit is connected, so that we have a variable resistance over here, and then we have a voltmeter which will ultimately measure the amount of the output voltage of this tachometer. So depending on, so this first of all, so firstly this tachometer is generally referred to as tachometer generator. Okay. So this is when we are talking about DC tachometer, it generally refers to DC tachometer generator. Okay. So as I have told, that the machine whose speed needs to be measured, that is usually coupled with the shaft of the DC tachometer generator. Okay, so the principle of operation goes like this, that when you have a conductor moving in a magnetic field, then from the conductor is moving in the magnetic field, then from using Faraday's law of electromagnetic induction, you can know that an EMF will be induced in the conductor, and the value of the magnitude of the EMF is directly proportional, or it depends on the flux that is linked with the conductor, and also and that will be dependent on the speed of the shaft also. Okay, so now in this case, when you have a tachometer generator, so in this case, the armature of the DC generator, that revolves between the constant field of the, so you have this, so there is a constant magnetic field provided by this permanent magnets, and the armature of this DC generator, that rotates in that permanent constant magnetic field. So because of this rotation, so there will be some induced EMF in the coil, and that induced EMF is directly proportional to the speed of rotation. Okay. So that means that, so that is the case. So now, so if you are applying this commutator in the output of the commutator and the brush, this whole mechanism, that is basically it gives an alternating signal. Okay, so but in the output, when we are trying to measure the output voltage, we want to measure a DC signal. Okay, so for this kind of mechanism, there is this commutator and brush. They work hand in hand. So we use slip ring kind of commutators which is able to convert the alternating current in the armature coil to some direct current. So this direct, once it is converted from an AC signal to a DC signal, then that DC signal or the DC value of the voltage, that is measured by the moving coil voltmeter, which is present in the electrical circuit. Okay, so now if the voltage, so the voltage will be accompanied with the magnitude as well as polarity. So the induced voltage can be either positive or it can be negative. So now the magnitude of the induced voltage, that is directly proportional to the speed of motion or speed of rotation, and the polarity of the induced voltage, which is whether it is positive or negative. Depending on that, you can say whether the shaft is moving in clockwise direction or the anti-clockwise direction. Okay, so if you can if you monitor the value of the induced voltage, so you will get an idea, or you will get the measure for both the magnitude of the or the speed of the rotation as well as the direction of the speed. So so now in this circuit, you see that there is a resistance also. So it is not, the output is not directly connected to the voltmeter. So why we are using a resistance? So this resistance is basically used because sometimes it happens that the current which is flowing, signal which is coming from the armature, that is very high. So the voltmeter, that is not, so if that is very high, so that means we will need to, so that means the voltage value will also be very high. So in order to control the amount of current which is flowing, coming out from the armature, such that the voltmeter that we are using, that is not damaged, and it is properly able to monitor or properly able to capture the output voltage, we are using a variable resistance. And by changing the variable resistance, depending on if the current is very high, so we will add like a higher resistance in series, so that the overall so the current which is or the voltage generated becomes a little less, and the voltmeter it comes in the range of the voltmeter, and it is able to measure that. Okay, so that's why we are using a resistance in series while measuring the output EMF. Now this DC tachometer, there are certain disadvantages also. Even though this DC tachometer generator, it has like linear characteristics and all, but still the problem is, since there is a commutator and brush kind of mechanism, so what needs to be done is that this commutator and brushes, they need maintenance. So from time to time they need to be cleaned, and they need to be maintained. So that maintenance cost becomes very high. And also the output resistance of the DC tachometer generator is usually kept very high as compared to the input resistance. So if there is some large current which is flowing or which is induced in the armature conductor, then because of that large amount of current, the constant magnetic field that can be distorted if there is a large current which is flowing through the armature conductor. So these are like certain disadvantages of DC tachometer, but these disadvantages can be remedied, or they can be overcome if you are using an AC tachometer. So AC tachometer, as the name suggests, that it is alternating current. Okay, so that means that in AC tachometer it has a stationary coil, it has a stationary armature, and it has a rotating magnetic field. So it does not have, unlike the DC tachometer generator, it does not have any commutator and brush. So that means the maintenance cost and all those things are taken care of. So those things are not applicable in case of an AC tachometer. So what happens here is that the AC rotating magnetic field here is that generates, it induces an EMF in the stationary coil of the stator. Okay, so once that EMF is induced, the magnitude and the phase, similarly here also In the previous case, we were more concerned about the polarity of the output signal and the magnitude of the induced EMF. Here, since we are dealing with an AC signal, so we will be looking into the phase of the output voltage as well as the magnitude of the output voltage. So the magnitude of the output of the induced EMF that will give a measure for the speed of rotation, and the phase of the induced EMF will give you the measurement of the direction of rotation Okay, so you can either use this magnitude and phase both together for measurement of this angular velocity. So what happens here is that as this rotor shaft, when this is rotating, the magnitude, so as we have told that the magnitude is directly proportional to the voltage, to the speed of the rotation. And here also you are getting an alternating signal, but here we don't have that tachometer, the commutator and brush mechanism to convert the AC signal to DC signal. So what we do in case of an AC tachometer is that we have a bridge rectifier, a diode rectifier circuit. Okay, so using this diode rectifier circuit, we rectify the AC signal of AC induced voltage that is passed through this circuit. It will give you a rectified signal, and that rectified signal then we will use a simple RC circuit, this RC capacitive filter, in order to smoothen out the ripples that are there in the rectified voltage. Okay, so because of this this RC circuit, it will, so the output here will come something like this. So output at this position, let's say 1. Then at 2, after this bridge rectifier circuit, at 2 you have used this, so this will be converted into a rectified voltage which looks like this. So here you see that there are lots of ripples over here. So using this diode or this capacitive filter, what you will do is that we will simply try to minimize the ripples as much as possible so that we get a more or less a constant value of the output voltage. Okay, so now there is one more type of AC tachometer. So this is known as a drag cup rotor type of AC tachometer generator. So here what happens is that we have two types of coils. Okay, so we have two states. So we have a reference coil and we have another coil which is known as quadrature coil. And why this is known as quadrature coil? Because these two are placed at 90-degree angle with each other. Okay, and the rotor is placed in the magnetic between the this coil mechanism. So there are two reference coils and there are two quadrature coils, and this is present in the in between the coils. Okay, so now this rotor here, in case of this drag cup rotor, so this rotor of this tachometer, that is made with a very thin aluminum cup, and this is placed in between the field structure. Okay, so now the input voltage that is applied at the reference coil and the output is measured from the quadrature coil. So in this case, this is your primary. So this reference coil is basically your primary coil, and the output, so this is the quadrature coil, is your secondary coil. Okay, so now the input is provided to the primary and the output is obtained from the secondary coil. So when the rotor is rotating in this magnetic field, so this, because of this rotation and the input voltage which is applied, there will be some output voltage generated in the secondary coil, and the value of this output voltage or the induced voltage, that is proportional to the speed of the rotation. So this is how the AC tachometer generally works. So now let's see how you can model a tachometer. Okay, so irrespective of whether you are dealing with a DC tachometer generator or an AC tachometer generator, the basic principle or the basic characteristics remains the same. So the basic characteristic is that the output of the tachometer, that will be proportional to the rotor speed. Fine. So if you write the expression, so let's say ET is the output voltage. So ET will be equal to some constant KT, proportionality constant KT into So if theta is the angular position, so that means derivative of the angular position will give you the angular speed. So you can write that ET will be equals to some constant KT into rotor speed or the angular speed. Now if you take the, so this is a time domain equation. So now if you take the Laplace transform of this equation, you will end up with this will be equals to this ET of S will be equals to KT into S into capital theta S for the first term. Okay. So now if you want to write that.
Ma'am.
Yes.
Ma'am, can you continue next class, ma'am?
You have another class after this?
Yes, ma'am.
Okay, fine. So actually this is the last. Okay, fine. I'll talk about this in the next class. And okay, so before finishing off, the quiz will be on Friday from 6 o'clock. Okay.
Yes, ma'am. Thank you.
Okay, and please try to practice some problems that we were related to the topics that we were discussing. And in case if you have any doubts while solving the problems or while understanding the theory, you can always contact me. So yes, is it clear? Is it clear in today's? Friday. Next Friday, yes. Today Friday and next Friday is 4th of February. So 4th of February will be your quiz for module 1. Okay, I'll post it in the group as well.
What will be the format, ma'am? Like MCQs or?
Mostly, at least for this quiz, it will be of MCQ type, but then you will have to solve the problems also. So because probably it will be like you have to do the calculation in your rough and then just whatever result you are getting, you have to select that. But you have to show how you have done so that rough copy that you are doing, that also you would need to upload. So just only by giving the correct answer, that will not give you the full marks. You need to show how you have got the answer. So that
the PDF one.
Sorry?
Like the PDF, I need to upload the
PDF.
Yes,
you need to upload the PDF where you have solved the problems. That also you need to upload. So the instructions for the quiz and all I will post by next week, early next week. Yes, ma'am. Ma'am, how much duration that quiz will be? Mostly not more than 1 hour. So around 50 minutes to 1 hour. Yes, ma'am. It should not. Okay, so that's all for today, and we'll meet again on Wednesday. Thank you, ma'am. Yeah, thank you.